Welcome to Week 1, Chapter 1.2, Expectations, Variance, and Covariance as Geometry. Last chapter, you met the expectation operator, conditioning, and the laws of iterated expectations and total variance. This chapter is narrower and, in the long run, more useful. It nails down the algebra of expectation, variance, and covariance, then reveals that this algebra is secretly geometry. Correlation will turn out to be the cosine of an angle. We anchor everything in Maya's question. She has money to split between two investments and wants to know how risky the combination is. In this opening part, we start with the one rule that never asks permission, linearity of expectation. Here is the result in one sentence. Expectation passes straight through sums and constants. The expected value of a times x plus b times y equals a times the expected value of x plus b times the expected value of y. And this is true whether or not x and y have anything to do with each other. That last clause is the trick, and it is the most overlooked fact in all of probability. Most operations require independence. Linearity of expectation does not. X and y can be the same coin flip counted twice, two assets that move in lockstep or two unrelated numbers. Why is it true? Expectation is a weighted average, and averaging is linear. Summing over the joint distribution, the cross terms never needed independence. Each value just got weighted by how often the pair actually occurs. The joint structure is fully accounted for, and it simply drops out. To see that the cross terms really do vanish, take the most adversarial case, let y equal x, two perfectly dependent variables. Then the expected value of x plus x equals the expected value of 2x, which is 2 times the expected value of x, exactly the expected value of x plus the expected value of y. The rule holds even though x and y could not be less independent. Now compare variance. The variance of x plus x equals the variance of 2x, which is 4 times the variance of x. That is emphatically not the variance of x plus the variance of x, which would be only 2 times the variance. Expectation forgives dependence, variance does not. That contrast is the hinge of the whole chapter, and it is why the variance section is not a one-liner. To summarize part 1, linearity of expectation says, the expected value of a weighted sum is the weighted sum of expected values, and it holds even when the variables are perfectly dependent. It never asks permission, but that free pass does not extend to nonlinear functions. The expected value of x times y is generally not the product of the expectations, and the expected value of a nonlinear function is generally not that function of the expectation. That gap is Jensen's inequality. Variance involves a square, so it is one of these nonlinear functions. In part 2, we use linearity to price Maya's expected portfolio return, then define variance and covariance, where dependence stops being free.